All right, I want to talk about network programming with the NetBurner. Actually, this will be fairly general because we're going to use the sockets interface, which you can program with sockets on Unix, Windows, Mac OS, and then it's supported on the NetBurner as well. First, I want to talk a little bit about there are two common what are called transport protocols that are used with the internet, TCP and UDP. TCP is typically used with data that has to be transmitted error-free. It's got error detection and correction built in. It's also a connection-oriented protocol. So TCP is primarily used for when you're transferring files. It's the HTTP and HTTPS are actually built on top of TCP. UDP is primarily for streaming that if an error occurs in the data, it's no big deal. You miss, there's a little bit of noise in the streaming audio or a glitch in the streaming video, but it's not disastrous. And then we'll talk about the Sockets API and how to use that. What's new here is actually making this initial connection with sockets. Once that connection is made, you just actually use the read and write routines we talked about last time to send data from one machine to another across the network. And actually the network could be even on the same machine. The client and server could both be running on the same machine, could be in the same classroom, the same university, the same city, or actually, across the world. That's what networks are intended for sending data between two devices that do not have to be co-located. So, we'll look at that and we'll see how to actually set up the NetBurner so that you can connect to it from the internet and actually connect to it and transfer data to and from the NetBurner from anywhere in the world. And again, this is fairly common with almost all new devices that are coming out, that there's some way to actually connect to them and control them, over the internet. Okay, so let's get started. I think I mentioned TCP and UDP already. TCP stands for Transport Control Protocol, and UDP is User Datagram Protocol. UDP is simple, unreliable, is a simple, unreliable datagram protocol. It's faster than TCP primarily because it's simpler. It doesn't have the error checking built in. Now you can work with UDP and build in your own error checking and make it reliable all on top of UDP. It's kind of a lower level, simpler protocol than TCP. TCP though is sophisticated, connection oriented, reliable. It does error correction and checking. So if you use the TCP transport protocol, you don't have to worry about errors occurring. Those are automatically detected. Retransmissions occur automatically if there is an error in a particular packet. And all of that is hidden from the programmer. You don't have to worry about it. And that's kind of the beauty of it. We are going to focus actually in this course on using only TCP. Okay. There's no guarantee that a UDP packet reaches its destination. So if you use UDP, you have to build in your own acknowledgement, retransmission, and things like that. You just send data out with UDP. You don't have to establish a connection and then end a connection. With TCP, you do. You actually will connect to a remote machine from one machine to another machine. It's called, you make a connection from the client to the server. And then at the end, when you finish your communication, you shut down that connection. But after it's established, it's open until you shut it down and continue to send data across that connection pathway. TCP actually provides sequencing that's actually not built into the internet. You can send two consecutive packets out from one machine. They might arrive at the remote machine in reverse order, but TCP will automatically resequence them so that they'll be put back in the right order. It also provides automatic flow control. If a server gets too busy and can't handle the incoming data rate, the client will actually be a request will be sent to the client to actually slow down the rate at which it's sending data. And the reverse is true as well. If you're downloading from a server, the server will slow down. It's a full duplex connection. You can send and receive data on the same socket, and again, what we'll be using are our read and write routines to send data across. And it really is just like reading and writing to a file once you get the connection set up. You can have, of course, you don't have just one data stream or one connection from one computer to another. CS Server can actually handle, for example, multiple connections from multiple different computers, or even multiple connections from the same computer. So all those connections from the same computer would all be coming from the same IP address. So how does CS Server handle multiple connections from the same IP address? Well, each of those connections is associated not only with the IP address, but also a port number. So every communicating client process would communicate to CS Server using a different port number, and then CS Server can use that port number to distinguish between those different processes and communication channels. Server processes also are assigned particular port numbers. So servers programs listen for incoming connections on well-known ports. So like, for example, FTP uses port 21, Secure Shell listens on port 22, HTTP listens on port 80. So your client process makes a connection to the server IP address and also the particular server port number, where it knows that the server process is listening for connections on that port. And so you'll see the details of that as we get into this. Now, these well-known port numbers are port number assignments below 1024, and on Unix systems, you actually can't just arbitrarily listen to on a well-known port. You have to have administrative privileges to listen on a port number that's below 1024. We don't want an ordinary user, for example, listening on the Secure Shell port and pretending to be a Secure Shell process and capture passwords and things like that. So, those ports are again secure. So if you make connections to the well-known ports on CS Server, that you're guaranteed at least that these are programs that are started by someone with system administration privileges. Now, port numbers above 1024, which we'll be using, can be used then for just ordinary user programs. So we'll write server programs that listen on a particular port number, above 1024, for example. And then our clients then will connect to those particular port numbers. Okay. So the socket API requires that network applications be written in what are called client and server parts. So these are separate programs, separate processes. There's not symmetry here. The server has to call certain routines to establish itself as a server. The client uses a different set of routines than to establish a connection to a server. Once that connection is made, both the server and client routine actually just use the read and write system calls to send data back and forth across the connection. Part of the difference is that a server will typically communicate with several clients. Again, these could be clients on different machines from different IP addresses, or they could be, multiple clients all from the same IP address. But a client typically makes a connection only with a single server. We'll start today and we'll write a simple server that only handles one client. Of course, and then we'll expand upon that and make our server a little more sophisticated so it can actually handle multiple clients, simultaneously through multitasking. Actually, there's a couple different ways to do that. We'll look at a multitasking method today, and then we'll look at another solution to handling multiple clients kind of sequentially from a single task next time via like a polling method. So we're going to use the Sockets API for all of our network program. It's kind of the standard for network communication. I'll put up a link to a good guide. It's fairly short. It's called Beej's Guide to Network Programming. If you want to dig into this a little deeper, you can by looking at that guide. I'm going to touch on just the basics here, just enough so that we can write the clients and servers and then get communication between them. But this API, it's kind of the standard for network communication. It's supported by all modern operating systems, and then it's supported on the net burner. It's also supported on RTEMs. Most real-time operating systems support this API as the default networking API. So on the client side, it's pretty easy to get established. You actually just make a connection to the server. So this is the connect is kind of like opening a file. Connect will return a file descriptor, and once we have that file descriptor, then we just read and write to that file descriptor to send data to the server. It's that simple. And then when we close the file descriptor, that breaks the connection to the server. So the client side code is pretty simple. The server side is a little more complicated because servers will typically have to listen to multiple clients, and so we need different file descriptors essentially for each of those different client connections. So on the server side, we have to go through a couple of steps, not just a single step. So first, the server will use the listen routine to listen to on a particular port number, often the well-known port number, for an incoming connection. The client makes a connection to that well-known port number. And then the accept routine then kind of pulls that connection out of from the listener and returns another file descriptor, and it's the file descriptor that we get from accept that we use to communicate with the client, and again just reading and writing data to the client. And then we wait for when the client actually closes the connection. That breaks the connection on the server side as well. So looking at these in a little more detail, on the client side, we have the connect routine. Again, here it returns a file descriptor. The first argument is the IP address of the server. Okay, and this is the port number we want to use on the local port number we want the client to use for communication. You can specify a particular number here. You want to use a port that's not already in use. Typically, we don't care what port the client uses, so you can use a 0 here and you'll be automatically assigned a port number. It's called dynamic assignment, and you don't really care what port, you just want an available port. Now the remote port is the listening port, so if we want to establish a connection to the FTP port, that has to be port 21, or the web server port, HTTP port is port 80. And then the fourth argument here is the timeout argument. Often that will be 0. We'll wait forever until the connection is made. You could optionally specify a timeout. For some reason, if the network's down, the server is not reachable, and then the client could just exit after the timeout occurs with a message indicating that it wasn't able to make a connection to the server. Um, Once we get this file descriptor, we just send data across using a read and write routine. Now, it is important to establish a communications protocol here. You know, who writes first, the client or server? You know, this is the case when you're writing both parts, both the client and server. If you're connecting to you know, a well-known server, you know, there's that protocol is already established, and you have to follow that protocol. But we're going to be writing our own clients and servers, and so you have to decide, you know, once that connection is made, who sends the first message across. You know, then you know, once that message is received, you know, how's the message terminated? Does every message start with the number of bytes in the packet, and then we keep reading until we read that many bytes? Or maybe we're using a 0 as our packet terminator, in which case we have to make sure that zeros don't appear in the data. Again, we've talked a little bit about this in the past, but it's very important that you know, as we proceed here, you come up with your own protocol for how the client and server transfer data back and forth. I mean, the issue again is if you send you know several thousand bytes across using writing from the client to the server, that data may be broken up into smaller packets, and then the server will have to call read multiple times to ensure that it's received all the data that's written by the client. So you have to have some terminator in the data that the server can will keep reading until it sees that terminator. Or again, you might use a header and first send across the number of bytes that you're going to send in the entire message, and then the server will know to keep calling read until it's read that number of bytes. And the same would be true for reverse communication as well. Okay, so here, looking in detail at these arguments, the address is the binary IP address of the server, and then the local port is the port to be used on the client. Again, typically, I'm just going to say use 0 here for the second argument so that you'll be dynamically assigned a port. The remote port is the server port to connect to, and then again, that has to be known. You know, when you write the server, you're going to listen on a particular port, and that's the port we're going to connect to. And then the timeout is the timeout and ticks to wait for the connection, or you can use a 0 to wait forever. Okay, on the server side, it's a little bit more complicated, although not much. The server first calls listen to set up a queue for client connections. Now, a computer may have several IP addresses associated with it. It may have several network cards. You can choose to listen only on a particular at a particular IP address. That's what the first argument is for. Or again, there's a special argument where you can say you want to listen on all IP addresses that is assigned to this particular server. And then this is the port that we're going to listen on. Again, for us, this will typically, you know, this will be a value larger than 1024. Not a well-known port number is what we'll typically use. And then you can actually in the listen queue, you can specify a number here, the maximum number of pending connections. So the client will be connected, but we won't start communicating with the client until it's pulled from this listen queue. So typically a max pending value here of 5 is often used, a relatively small number. So you can connect, but you can't communicate until you've been moved from the listening queue into the accepted pool. So a file descriptor is returned. That's this listening file descriptor. That's then used passed to the accept routine to return yet another file descriptor that we use for the individual clients. Okay. So we call listen early on, and then as we're then in in a loop, we would typically accept connections from this listening file descriptor, and then for each of those connections, we'd be given a new file descriptor. Okay, so the arguments in listen. Again, address is the binary IP address that we want to listen on. You can use this in address underscore any. It's a macro. I think it may map to 0 to accept connections on any of the listening addresses. And then port is the port that we're going to listen to. And then max pend is the number of pending sockets. Okay, a value of 5 is typical. And then the server calls the accept routine to accept client connections. Again, this would typically be done inside a loop. So the first argument is the listening file descriptor that we get back from our call to listen. And then you can pass pointers to IP address and word data types here to get the IP address and port number of the client. Typically, you can just use null here. You don't really care about what those IP addresses are. You really just want this file descriptor. That's how you're going to communicate with the client. But if you want that information, it is available. You can get that and print that out. So accept will actually block until a connection is made. When it unblocks, you've got a file descriptor, and then you can use that file descriptor then to send data back and forth to the client using read and write. Okay. So details on the arguments here. The listening FD is the file descriptor returned from the listen command. Address and port are return arguments that contain the IP address and port of the connecting client. Again, often you can just use a null value for those because we don't really need that information to communicate with the client. You may want to get it and print it out as useful information as part of the server, but you don't really often need that information to do communication. And then timeout's the number of ticks to wait. Okay. There are a couple of utility routines that are available in the net burner that are not part of the Sockets API. I mentioned on the very first slide, I think I showed a couple of references that are useful. This is the net burner programmer's guide. Again, this is in the nburn docs directory. All the information we're talking about today actually comes from chapters 11 and 12 in there. So these are the specifics. They have some examples here of writing a net burner server and then writing a net burner client. And then it also shows how to actually, there's an example on writing a Windows server. I'll provide example code for that. There's not much difference actually between writing a Windows server and writing a server for Linux or Mac OS. And then the other documentation is in the NetBurner runtime library, and in particular, chapter 26 here. Here's where you'll see the documentation on listen and accept, which are the routines used by our server, and then also the connect routine that's used by our client, and then some other various routines that are available. In particular, host to network long, host to network short, network to host short, network to host long. I'll talk about in just a second. So back to the slides. Okay. So show IP will actually convert a binary IP address to dotted quad notation, and it displays that actually on the serial port. So you don't even have to call a print routine. And then the ASCII IP routine converts from dotted quad notation to a binary IP address. This is useful because a routine like this is useful because you may want to specify a server as an ASCII string, and which is what this dotted quad notation is, and then this will convert it to the corresponding binary form. Okay. One issue that you do run into with IP addresses and also port numbers is that there are different architectures that are used by processors. There's what's known as big Indian order processors and little Indian order processors. Intel processors are actually little Indian, which means that the most significant byte in a 4-byte int is actually stored at the higher address, and the least significant byte of a 4-byte int is actually stored at the lower network address, so it would appear actually first in memory. Big Indian processors store the most significant byte at the lowest memory address. So if you looked at this particular IP address in memory on a big Indian processor, you would see the corresponding binary value of 10 in the first byte, the binary value of 5 in the second byte, and the 50 in the third byte, and the 100 again in binary form in the fourth byte. But on an Intel processor, these would actually be stored in reversed order. When you looked at, if you did a memory dump, you'd actually see the 100 first, then the 50, then the 5, and then the 10. Well, that's a problem when you're sending data between computer systems. There's in the packet that's sent across, we send the IP address of both the server and the client, and stored as a 4-byte integer in the packet. Well, it has to be in a particular order. That's known as network byte order, and it's actually the same as big Indian order. So you might think that in order, if you actually had these stored in separate bytes, that you could convert this particular network address to its binary equivalent by shifting the 3 bytes to the left and adding 5 after it shifted 2 bytes, and so on and so forth. This will work on a big Indian processor. It doesn't work on a little Indian processor. You'd actually have to shift the 124 bytes to the left to put it in network byte order. So fortunately, there's a solution to this problem, that's architecture neutral. You use host to network long and network to host long. So for any binary IP address, you can convert that to network order using the host to network long macro, and it will do the correct conversion regardless of whether you're on a big Indian or a little Indian processor. On a big Indian processor, it won't do anything, but on a little Indian on a little Indian processor, it won't do anything. Got that backwards. On a big Indian processor, it won't do anything because big Indian is already in network order. And little Indian processor, it'll swap the bytes back and forth. Same's true for network to host order. On a big Indian processor, this doesn't do anything, but on a little Indian, it will swap the routines. But you should always use these to make your source code portable between different architectures. So again, this may be one of the first times you've actually worked with a big Indian processor. The net burner, the cold fire processor that's used on the net burner, is a big Indian processor. Okay. I have the same issue with port addresses. They're actually 16-bit integers, so you only have to worry about swapping 2 bytes instead of 4 as in a network address, but there are corresponding host to network short and network to host order routines. You have to pay careful attention to the documentation here to see if a particular needs the IP address or the port number in network order or host order, and most often the routines will ask for them in network order. So you often have to call host to network short or host to network long, perhaps, to switch the bytes into the proper order. Okay, that's it for today's lecture, and I have another little video to go along with the exercise today.